very happy to introduce Chris Russell, who's going to talk about explainable AI. So Chris, over to you.
Great, thanks Mark. Okay, so I've been told this is a very diverse audience and like this big mix of people from all sorts of disciplines, so I can't rely on any mathematical knowledge or any legal knowledge. And that's good, because what I'm going to mostly talk about is work I've done, which is cross-disciplinary anyway. It's been with ethicists and with lawyers, and we've been sitting down with them and coming up with what are definitions of explainable AI, which we can actually generate, like work as concrete systems and meet the needs of everyday people. So let's just kick off with like big overview of machine learning, which hopefully you're up to date with, right? So the problem of machine learning, for about 50 years, what happens is we have this endless stream of data coming in. We do something Fei-Fei Li likes to call machine learning mumbo jumbo. And at the end, you get back a classifier, right? And for about, which says like, yes, you should get a loan, or no, you shouldn't, or something. It does something with the data and makes a decision about it. For 50, 60 years, our big problem was, how do we actually learn a classifier, right? And now we're getting to a point where we have enough data, we have enough infrastructure, and we have enough machine learning knowledge that these things actually work, right? For particular limited circumstances, you can say, like, we can actually learn what we want to learn. So now we have a new problem, which is, what does it do? Like, we've gone through, we've trained this, and like, it makes a decision based on some data. And you're like, why did you do that? What just happened, and why are you doing it? So what's important to say is like, okay, now this is a big problem for machine learning. Sure, fine. But it's not just a problem for machine learning, right? So in general, like, you go to a bank, you talk to someone, and you say, can I make a loan? Now, back in the day, it used to be an individual would make a decision by looking at various factors and then coming up and going, yes, no, whatever. And you'd be like, but why? And generally, if you ask a person to, they've made a decision about you, and you're like, well, why are you doing this? And the same thing now, you go to a company and you say, can I have a job? Can I have a loan? They talk among themselves, they make a decision, and you're like, why? What are the factors that led to this decision? How can I change it? And it gets more and more nebulous the bigger the systems are you deal with. So if you start looking at economic factors and like in general, like trying to find a job somewhere in the economy, you have all of these, I can't even find clip art for this, you have companies interacting with each other and playing off each other, leading to market forces, and something happens. And you have these big systems which you really just don't understand, and somehow these decisions are coming out, yes or no. And you're like, so what's going on? Why is it happening? And how can I understand it? And the important thing to say is machine learning is easier than all of these problems. And the reason is we might have these impenetrable black boxes, which are used to make decisions about them. But the nice thing about these black boxes is they're honest, they're reliable, and they don't get bored. So you take the box, you change the data, you ask it, what would you do now? And it will give you an honest answer. If you do this to a person, they tend to make things up. If you ask to companies, they shut things down, they stop responding to you. It's only by having complete control over a system that you can actually check things, you can validate things, and you can begin to understand why things are happening. So machine learning is a much easier problem than the general, like, why are decisions being made? So yeah, given that, can we actually explain why certain decisions are being made? And then at that point you're like, well, okay, everyone agrees that it would be nice to know why these decisions are happening, but what does explain actually mean, right? And is it really going to be useful? And does it matter if we have explanations or not? And for a long time, this has been like a fundamental problem, because in order to make something simple enough that we can understand it, right, you often have to reduce its accuracy. So there's this trade-off, like, do I want a really good machine learning algorithm I can't understand? Or do I want something simple enough to understand where its performance is worse? And fundamentally, like, the whole like explainability is about getting rid of this computer says no, right? It's like you go through, there is a decision made about you, and you're like, well, what happened? Computer says no. You get no feedback, you can't challenge it, you can't change anything. And it's just like some kind of interactivity and telling people something about why things are happening, which makes them feel like they are part of the system, and it's not just this impenetrable brick wall blocking them off. In terms of useful, right, so this is a big question. Like, so in terms of cancer diagnosis, would you rather have an algorithm which no one can understand how it works, but is very good at detecting cancer? Will spot it with So like 95% accuracy, if it says, yes, you've got cancer, then 95% chance you've got it never makes a mistake and says, no, you've not got cancer when you don't, but you don't understand it. Would people be happy with this? Should we do a show of hands? Who'd be okay with that? Like most of you, I guess, or more than half anyway. How about if it predicts crime hotspots? So we're sending the police out to where there's high criminal activity and we want to stop it, right? Suddenly this becomes a lot harder to understand and reason about, because if you send the police anywhere and you tell them, find people to arrest, they can always do this, right? So in some sense, there is no real ground truth, right? You send people out, or you send the police out into the world to particular locations, wherever they go, they find crime and they can stop it. And you end up with these feedback loops quite often. And you have systems which will just reinforce existing prejudice. They go into poor council estates, they pick on minorities, and they keep driving towards them. And in these kind of situations, it becomes a lot more important to actually understand, how is the algorithm making decisions? Is it reinforcing biases? Is something going wrong here? Okay, and yeah, so as I said, the real reason this is fundamentally hard is because the best algorithms don't fit in our heads. So this is going back over 20 years now to like one of the first convolutional neural networks. And this is now considered a toy problem, right? So it takes in these tiny black and white images, like a picture of a letter A or something, and it correctly recognizes it as a letter. And saying like, yeah, this is definitely an A. And the way it does this is it goes through several layers. So it's looking locally for edges, and then this pushes through, propagates to another layer of a neural network where it's looking for junctions and larger edges and how they fit together. And then it goes through, and then at the top, there's like this giant interconnected neural network which pulls everything in, it's fully connected. And so this is something we talk about as a small toy problem, which means it's got 1 million different parameters in already, and it's got many different layers. And the actual reason it makes a decision is a combination of factors will come together. At the end, it's like, we multiplied this bunch of numbers together, we pushed them through a function, we multiplied them together again and again and again, and at the end we got out yes or no. And like fundamentally, there's 1 million different numbers here, and people can think of, hold maybe 7 different numbers in their head at any point. So any explanation we give people about these is it's either incomplete, it only tells them something about the structure of the neural network, or it's an approximation. And it's sort of like, it gives people a false sense of security and confidence, and it tells them something which is not always true. And so this is where we're at now. Instead of that had 3 different layers of convolutions, I think, leading up to it, and now we're dealing with 512, or thousands and thousands. And it's the same structure, just duplicated again and again. And we're actually talking about billions of different numbers, and there's absolutely no way we can describe this. So yeah, and because there's these complex interdependencies between the items, you can't just take out summary statistics and expect to understand what's going on. So, but at the same time, right, people can explain their decisions, right? And the neural networks we have in our head are a lot more complicated than these things. Even if they've got 1 billion different numbers, that's still nothing in comparison to what's going on. When we look at stuff, we weigh things up and we make decisions. So somehow the notion of explainability doesn't depend on the complexity of a classifier directly, right? It's something you can actually you can get away from it somehow in a way that people are happy with. So yeah, in order to answer, like, do we need explainability, you have to stop and actually take time to say, like, what it means to different people. And this is interesting. This is why it's worth talking to you guys and cross-disciplinary thing, because what you find is that scientists, mathematicians, and engineers have a fundamentally different idea of what an explanation is to everyone else in the world. Okay, and so in order to decide if we're going to explain AI, we have to actually stop and say, well, what kind of explanations are we talking about? Because you go to machine learning people, I want an explanation. They go away and they do something. And this something is completely incomprehensible to everyone else. Like, you cannot give these explanations they come up with to sort of an elderly person, to your grandma, or maybe you can, if your grandma's a spectacular mathematician. But definitely not to a judge or to a lawyer. These don't function as explanations where people can go, oh, now I know what your algorithm's doing. So what's worth doing is when we try and explain how decisions are being made by algorithms, we have to answer a bunch of questions first. We have to say, like, who is the audience we're trying to reach? Okay, why are people wanting these explanations and when do they want them? If it's like, I've just asked for a loan, I haven't got one. Do they want something back which will let them change the outcome of the loan? Or do they just want to understand like how the system works as a whole and it's fair for them? Depending on what you think the answer is to this, like the explanation you will give people changes each time. And so you're also faced with questions like, do I care about how the model works as like a general principle or how a particular decision was made? And as such, like what information should I be providing to people? Okay, so you end up with these like wide range of questions like, why is the system behaving like I did? Which is important if you're trying to debug a system, you're trying to improve its accuracy somehow. And is the system working as intended? Right? These are things that, like, as an engineer, you might care about. And also, like, just sanity checking. Like, does the decision feel sensible? Is this the right sort of thing that should be happening? At the same time, you have legal concerns. Like, is this system explicitly racist or sexist? Is there something I should be doing which I'm not doing? Is there indirect discrimination here? And, like, as an individual, am I being treated fairly when these decisions are being made about me? And then there's this, like, okay, like I came and I asked for a loan and you said no. How can I change this? What can I do to get the favorable outcome I want? And answering these questions, each of them is very hard. Each of them requires a completely different explanation, right? There's no general one-size-fits-all solution to these problems. So, yeah, what do scientists and engineers do? And the current methods, which are popular in explainable AI, what they do is they take these big, complicated models they can't understand, and they build a simplified approximation of it, right? As a scientist or an engineer, mathematician, this is what you're trained to do from the beginning, right? You have a phenomena you want to understand. Like, if you put a weight on a spring and you flick it gently, it wobbles. And you're like, well, why does it do this? And immediately what you do is you build this very simple physical model. You come up with Hooke's law, you start doing second order differential equations, you get back a sine wave, and you never wonder about all of the big complexities, like you ignore non-Newtonian physics, you ignore shearing, plastic deformations, all of this stuff. It's like, what is the smallest, simplest approximation that gives me the phenomena I want to know about and how to do it? And machine learning scientists do the same thing, right? They go through and they go, okay, let's build a simplified approximation of this big non-linear complex system, and we'll approximate it as a linear function about a particular data point, or we'll approximate it as a decision tree, a bunch of yes-no binary decisions that shunt you down somewhere and say why a particular decision was being made. And these are used either globally, so it's like, well, we'll approximate this huge function we don't really understand over the whole domain as a simple linear model, for example, or instead around a particular decision. Like, I decided not to give you a loan, and what I can do is I can give you a linear model, which is a close approximation, tells you how people who were similar to you would be treated, and what factors are important for making the distinction between these similar people and you yourself. And yeah, so this is basically these approximations as a scientific model. And we are creating these simplified approximations, more complex models, yeah. And so this is great for basically training data scientists, and for, as scientists, trying to reason about what is our classifier doing, how does it work. We can break it down into a more simple model, and we can start to understand and reason about why it works and where. Okay. However, the big catch, and this is a famous quote by a very famous statistician, which is that all models are wrong, but some are useful, right? Anytime I give you an approximation, what I'm actually saying is like, there are some data points for which this approximation doesn't work at all, right? So anytime I'm trying to explain something as like a simplified case, you have to worry about, well, how accurate is my simplification? Over which domain does it actually work? How far can I stretch out before it starts breaking down? And how complex is it, right? So if I make something which is as complex as the underlying phenomena, then I can accurately describe it. But every time I give a simplified approximation, there's a trade-off going on. And as with when you're doing science, right, you need to know over which domain these approximations are reliable, where they break down, and where its behavior is uncertain. And there's a fundamental problem. in all of these modelling approaches, which is no one considers these issues at all. They just go, here is an approximation, and you're like, how far can I trust this? When should I stop using it? And people can't actually tell you. There's no research into this. I mean, it's interesting because if you take the difference between an engineer fresh out of school versus an experienced professional, the fundamental difference is that they will have the same tools to a large degree. They will be able to build the same approximations of what's going on, but they will know, like an experienced professional has had a lot of experience using these models, they know their limits, right? They know this is trustworthy over this particular domain, and when I go beyond that, it breaks down. And this is something which is very hard to teach, right? It's something you only learn from practice and experience and doing. And so to just give people, like, here is an approximation of your model with nothing else, no guidance, is extremely worrying. So as a very rough example, suppose we have this nonlinear function. We have a quartic, it's got a couple of bumps in, and we're trying to build a linear approximation of it. What you find is that as you change the domain, the region over which we try and approximate it as a linear model, it fluctuates wildly. So if you just do a local approximation of a single point, you use a gradient, you get this thing in the top left. Okay, so you get a line sloping up. As you slightly widen the line, so you're now trying to cover a region which goes up and down and oscillates and kind of cancels out, you find that a flat approximation is much better. As you stretch the domain further, suddenly it swings the other way, and it becomes unstable again. And then as you pull out to a much larger domain, you find a flat function is again the best approximation for this. And somehow, like when you're saying like, oh yeah, think of this function as a linear approximation, you have to somehow convey these uncertainties to people. Now, the people who are actually working in this, what they're more worried about is high dimensional issues. So it's points which are tied together. So if I have a function which says, I take value 1 if input 1 and input 2 are both on. Okay, and I take value 0 everywhere else. How do you actually express this as a very simple linear function? And basically there's a bunch of different trade-offs you can make, and sort of like, how do I weight points individually? So something called LIME goes through, it weights the original data point the most, and then you have this gradually decaying sort of exponential like weighting on stuff as they get further and further from the point. Deep lift ignores that. It's a very simple heuristic that just looks at the closest points and approximates those well. So it would completely fail to find like these AND functions. It would ignore them entirely. And then Shapely Values does something else, and it averages over the entire domain. So you end up with these kinds of trade-offs, basically, where essentially you can think of Deep Lift as doing this tightest, most local approximation. Shapely Values are doing this thing at the end, where it averages over the whole domain. And at some point, nothing is really telling you what's going on. Okay, in contrast, when you talk to people and you ask for an explanation, they give you something very different. Like, no, you say like, I don't know, why did you get in a car crash? No one gives you a linear approximation of the road conditions. So what people tend to do is they talk about a causal chain and how necessary particular causes were to an event occurring. So in scientific setup, you might want all possible causes of an event, but generally when people are talking, they'll tell you one or two things, which if they hadn't happened, the event wouldn't have gone through. And so these everyday explanations you get focus on why particular facts occurred rather than sort of like general scientific relationships or these approximations. And what happens is everyday approximations, they have three properties. The explanations people give as an individual to each other. They are contrastive, they are selective, and they are social. And in particular, explanations are sought in response to counterfactual cases. So people don't just say why a particular event happened, but rather why an event happened instead of some other event. And the perceived abnormality of an event drives the request for explanations. Particularly, so something happens and it surprises you. You didn't think that would happen. You're like, so why did that happen? You actually ask for an explanation. If you already expect the behavior, you don't care about the explanation. This is what you thought would happen anyway. And at the same time, causes which are unnatural are preferred. So For example, if you have a car crash and people are like, so why did these two cars hit each other? One explanation is always like, well, if I'd left home 5 minutes later, I wouldn't have had this car crash because the other car wouldn't have been there. Right? This is completely valid. No one will ever give that because these fluctuations in time are completely normal and expected. So instead, what people do is they talk about swerving, they talk about slipping on the road, things which don't normally happen. And it's these unexpected events that people look for and drive explanations. So yeah, as said, these explanations are selective, right? A fully causal explanation is exceedingly rare and not expected. And so you select relevant things. So there's a famous quote by Carl Sagan which says, to create an apple pie from scratch, you have to invent the universe, right? And to explain an apple pie in the same way, you have to explain the entire universe. It's like, where did these fundamental physics constants come from, which gave rise to this phenomena, this one, which finally led to me making an apple pie, right? That is the full scientific explanation of it. But if you say, why did you make an apple pie? What you want to hear is, my mum was coming over and she likes apple pie. So it's this selection and this model of having the person you're giving the explanation to and like meeting their need and telling them, here is one factor it depended on. So for example, you have a glass on the table and you go and it breaks and you're like, well, why did it break? And it's like, well, it fell on the floor because gravity exists, and then the marble it fell on is harder than glass, right? These are all valid explanations. Or maybe, it's because my cat is antisocial and knocked it off the table. And it's this final one, this is the relevant phenomena, which is contrastive and selective. It's explaining why that glass broke at that particular time versus the many other glasses I put on the table safely. Okay, and so these explanations are social, right? They come in the form of a dialogue. There's people talking back and forth between each other, and the information is tailored according to what I think you care about and what I think you're going to understand. And because of this, explanations are discursive and they're iterative. It's not just like, I blast you with information, like in a seminar. It's more like a discussion or an argument. Ideally, it's like someone on the stand in a law court, right? It's like, so why did you do this? I give you an explanation. The lawyer comes back to me, they interrogate me, they ask, but what about this factor? What about this factor? And they make sure everything is there. And because of this, you get maybe not disagreement, but conflict. And the implication, as we're trying to work on what explanations we should give people, is more work needs to be on methods which are for the layperson, right? Instead of these big scientific approximations and these linear models, we need to give people counterfactual explanations, which I will get onto next, and these sort of like selective and social explanations which tell people what's going on. So I'm presenting work slightly out of order. So basically, just gone over one paper which came out of this second one, but it was sort of like, what happened is I sat down with lawyers and ethicists and we came up with a way to give people explanations that look like this. So you have an automatic decision-making algorithm and you're like, why is it not offering me a loan? And it can say, you were denied a loan because your annual income is only 30K, right? If instead you earned 45K, you would have been offered a loan. And these are things which we can do automatically with neural networks now. This is now cited in the guidelines to the GDPR as this is a good form of explanation to give to the layperson. This is something to think about. And it's also now part of the TensorFlow machine learning system. So what happened is we sat down for many days, basically, and we had huge arguments about this because the lawyer was like, no, explanations are really useful. And they tell people what they want to know. I was like, no, they're these approximations. And you can't give someone a linear model and then expect them to understand how and why decisions are being made about them. And it was finally we came up with this sort of counterfactual notion, which has existed in philosophy a long time as a way to resolve the issues. So these counterfactuals, they date back to the 70s and famous philosophical work by Lewis, who came up with this statement that if kangaroos had no tails, they would topple over. And this is interesting, right? Because it kind of sounds like nonsense, but we all agree what it means, basically. And what he was trying to do is put like the underpinnings underneath it and to show what it means. Because this statement is logically, it doesn't have to be true at all, right? So, I mean, kangaroos which are sitting down won't fall over if they've got no tails. You consider like a different hypothetical world where kangaroos exist, but they don't have tails, and they fall over. And you're like, well, sometimes this is true, sometimes it's not. But everyone can look at the statement and more or less agree what it means. And it makes sense that there's something going on here. And the way Lewis formulated this is he said, what these counterfactuals do is they talk about a closest possible world. So a world which is as similar to ours as possible, in which kangaroos have no tails. And then we agree that then they would fall over. And what's nice about this is you can actually take these kind of statements and you can turn them into explanations. So you can say kangaroos don't fall over because they have tails, right? This is just a rephrasing of the same statement. And implicit, there is this notion that if they didn't have tails, they would fall over. And what's good about this is this tells you a lot about how kangaroos move without requiring you to understand their biology in any detail. So why are these things useful in the context of explainable AI? And there's like 3 big reasons we could come up with. Like, firstly, they help you understand decisions. They help you alter future decisions by telling you what to change to get an outcome you want. And they let you challenge decisions. If you get back offensive or abhorrent counterfactuals, like, I would have offered you a loan if you weren't black. Like, this is immediately something you can get your teeth into. You can go, this is not right. We need to change the system. Like, something is broken here. And you can take it to people, you can complain, you can contest in a way that you can't. So let's go through like a toy AI example. So we have a security guard, right? And we deploy the system, we push it out into the real world, and we're faced with unexpected behavior, right? So it falls in the fountain. And you're like, okay, well, what happened? Like, I don't understand robots, but can you explain what's going on in a way I can actually fix it? And so you want to understand the behavior, and this is where counterfactuals come in. And you can say instead, if the robot saw the edge of the fountain, would it have stayed out? Or possibly if the robot had not been pushed into the fountain, would it have stayed out? And what this understanding lets you do is it changes the system, right? You can alter the behavior, you can mark the fountain edge, you can get your toy robot security guard to be followed around by a real security guard who will stop people pushing it in the fountain. All right? And you can figure out what's going on. And even if this doesn't work, like if it's too hard to keep the robot out the fountain, you can send it back. It gives you these tools to challenge the system and to change what's going on. And what's really important is at no point do you need to understand how a robot works in order to use these counterfactuals and to figure out what's important. So here's where the maths comes in, basically. So what we were saying is that Lewis formulated these counterfactuals as the closest possible world in which you get a different outcome, right? And you can write that down. So we have some kind of classifier, like, should I get a loan or should I not get a loan? Okay, and that is, we can say, okay, I get a new data point comes in, this changes the classifier response so I get the outcome I want. Okay, and now all I have to do is I need to find the closest possible world which will actually do that. Okay. And then you're like, okay, well, what does closest mean? And this is actually where philosophy as a whole got stuck. They were like, they're really happy with this definition of, oh, we should think about the closest possible world for counterfactuals. But then they couldn't actually come up with a coherent definition of what closest should mean. So as a mathematician, what that tells me is I'm free to pick the definition which works the best for my problem. And I can just make something up. And so what I did is we were looking at how, so now think about how you change a piece of data in order to get the outcome you want. And what's really important here is we make as few changes as possible, right? If I take a data point and I change everything in it, I say, oh, okay, well, I would have offered you a loan if you earned more, if you were taller, if you lived somewhere else, this, that, the other. Like 100 different factors. It doesn't fit in your head again. You don't understand why these decisions are being made. It doesn't actually help you. So what you actually need is you need sparse counterfactuals. You need to change only a small number of factors in your thing in such a way that this happens. And one of the ways to do this is you use a distance function called the L1 norm. So typically we use Euclidean distances to measure everything. which you can think of it in 3D space. We're saying everything on the surface of a sphere is the same distance from the center of it. What the L1 norm does is it prefers spiky objects, basically. It says, instead of like looking at the surface of the sphere here, it looks at the surface of a tetrahedron as its equivalence class. And this means that basically the corners of it stick out the most. So the corners of it are more likely to intersect with other objects, and this implicitly gives us sparse counterfactuals. Very sorry. I think given like the wide spread of knowledge in the room, it's like magic happens. Use like L1 distances to get sparsity, I think. Imagine we've got this lumpy function here, and we've got a data point which is in the top right. Okay, and what we want to do is we want to somehow find the closest point on this black line. Okay, it's sort of like pushing through the black line will give you a new counterfactual. It will tell you like, yes, this is what you'd have to change to get a loan. So what we do is we start at the point and basically we grow out this spiky tetrahedra. So we start here. These are the points which are all equivalent in distance from x1 under this, from the initial point under this measure. And we systematically grow it out until it collides. And you can see here, because it's pointy, basically, it's more likely to hit with a corner and therefore to induce sparsity. This is not always guaranteed to happen. If you're in the wrong location, quite often you can get dense counterfactuals. So what's nice about this is we can actually use exactly the same tools that we do for training neural networks to actually find these sparse counterfactuals. So basically, we took the formulation I gave you before, where we said, okay, we've got to change the classifier function so that it equals white. And we turn this into something which is called a Lagrangian constraint. And then we have subject to minimizing the distance as well. And basically what we do is we go through and we use the algorithm which trains neural networks, and we use it to update the data point x. And it's like find the closest data point for a particular lambda which minimizes the distance and gets us close to the target. And then we increase lambda. So this makes it a tighter constraint, and it pulls us more and more towards satisfying this as a hard constraint. The fact that f of x prime equals the target value y. And what's great is, we can solve this using backpropagation and gradient descent, the tools which people have hammered on for years. Like they've got probably millions of person hours in building these tools which are reliable and trustworthy, and we can take them and use them to generate explanations. So they look like this, for example. So I should say this is an example taken from an old, very racist data set. It's in the US, set back in I think towards the end of segregation, basically, where people who were black were allowed to go to law school, but they couldn't go anywhere good. And as such, it was very easy. Like if you knew someone was black and they were going to law school, they were probably going to fail. And when you train the classifiers on these old historic data, they pick up on this and they go, well, you're not going to be able to get into a good school, and therefore I should not expect you to do well. And so what you find is you get these counterfactuals, which if you're white, they look great. They all make sense. They say things like, oh, your law school entry was 34. Hang on, where are we? So for the first person, they had 39, so they're predicted to do better than average. If it dropped down to 34, they'd do worse than average. For, hang on, that's lined up wrong. Okay, for person 2, again, it looks good. It's like, okay, well, if your law school dropped down, then we would expect you to do better. For person 3, suddenly you start seeing these issues. It flags as a counterfactual. It says, oh, I'm sorry, but we would only predict you would do as well as average if you were white. And it immediately tells you something is wrong with the system without having to require you to understand the system and go through it in great detail. You can flag these things as like explicitly racist and wrong. And they give you grounds to contest. They tell you, oh, something is broken in the world and we need to change it. We also ran it on sort of simple, like diabetic data sets. So it was looking at things like, it had 8 different factors, like how many times you'd been pregnant, what your age was, your BMI, and so on and so forth. And it did basically linear regression to predict whether or not you were going to get diabetes. When you generate these counterfactuals, it finds that your insulin levels and your blood sugar are the most relevant factors. And it starts giving you these counterfactuals in terms of, if your insulin level was lower, you'd be in the at-risk group. Or if your blood sugar was lower, you'll be out of it. And this is similar to the risk factors already used by doctors to communicate, right? When you're talking to a patient, you say something like, if your body mass index is greater than 40, you're morbidly obese and at greater risk of ill health. It's these kind of factors, and you're like, your blood sugar level is too high, therefore you're at risk of diabetes. But the difference is that these are now customized. So they take into account all of the other factors and they fuse them together and they give you a personalized recommendation of like, here is the tipping point at which you become at risk. So let's see, how are we doing for time? I'm gonna skip this bit a little bit. Hang on. Yeah, let's just go show some pictures instead. So I said this was solved, right? And if you take anything home from these messages, like when people say something is solved, they mean it's solved for the particular problems I worked on. Like when you try and generalize this beyond where I've worked, these relatively small data sets, you start running into problems. And one of the issues is with this sparsity and how you can actually find sparse solutions. So like the objective I wrote down is it's ideal, right? And it will, if you can solve it exactly, it will give you sparse solutions. But the solutions we find, it's not just a function of the objective we're trying to solve, but also how well we solve it. And can we do better than using these standard off-the-shelf things? So what we actually came up with is, I will gloss over it a bit, but local approximation, where we're iteratively solving local problems, which are always in a sparse way, and we update these over time. And this means that you're guaranteed to always have a sparse solution at every step. So this really matters. So working with other people who are interested in credit data, they kept changing these different metrics and saying, like, instead of using L1, we'll use something else weighted differently in order to get as much sparsity as possible. Because they were saying, like, we have this average complexity of around 5 different factors are changed each time. What we found is that actually if you just optimize it properly in the first place, you bring down the average complexity from these 5 different factors to just 1.3. So you can massively sparsify stuff just by correcting things and optimizing them properly using the new method. You see this with like random polynomials. So we're like, okay, I'll give you a quadratic equation, find me some zeros in it, changing as fewer factors as possible. And what happens for these standard solvers, which we're used to, something like Adam or gradient descent, is they still tend to find these dense solutions. So that as the complexity of the polynomial gets larger and larger, they change more and more factors, and it becomes incomprehensible how many things they've changed in order to find a zero. Well, if you search clearly and formally, you can always keep it capped. So you can easily have millions of different variables changing and still find something simple. So what happens is, if we're working with a neural network, which is used to classify an image, so we go through, we run VGGNet, which is, it's standard, basically. On this image, it comes back and it says, it's an Alsatian. We now run this counterfactual generation using the standard solver I talked about earlier, and it says it's now a Malinos, which is another type of dog, very similar to a Alsatian. And you're like, okay, why did you do that? What are the differences? And you see the differences on the right. And it's like, okay, you changed everything. Right, this is not a sparse counterfactual in any sense of the word. And you go through and you try it with another solver. So, hang on. I've lost an image. Okay, you go through, you try it with our solver, and you get this. Okay, and what you see is, instead of changing every pixel in the image, it's drawn this small round object on the middle of the nose, and there. You can see it sort of like pulled out in contrast as the difference. And to me, I was looking at this and going, you know what, this looks kind of like an eye, maybe. Right? This is one of the things, actually, like as you stare at these pictures, it's like staring at clouds. And you sort of like can convince yourself that there is something meaningful going on here. And I was like, I wonder what a Malinos actually is. And so I Googled it, and the first hit is, this is the difference between a Malinos and a German Shepherd. And it's basically the same dog, at least the upper torso, but just with more distinct eyes. And so, in some sense, it's like, I don't know, it feels a lot like reading tea leaves, in some sense. Like, is this really a good explanation for what's going on? Does it really tell us how the classifiers work? It feels meaningful, at least. It feels like it's telling us, like, if this dog had more distinct eyes, if we drew in another distinct eye, I would believe this is a Malinos rather than a German Shepherd. And so if you work with clustered images, so you've got object with person in and a bunch of different classes, and you're like, okay, if I keep adding stuff to it, if I try and generate a counterfactual, will it mask out one object and then tell me about the others, or will it change one and then tell me about the others? And so you try this with like the standard solvers and something like ADAM, and it changes everything, just as before, and you've got no idea what's going on. Somehow we can switch this dog, the dog in the background has been labeled as a coyote, and we can make some changes everywhere, and we find out it's a wallaby. The second one down is sometimes it's a slightly better solver. And this is giving you a sparser solution, and it's saying change two different areas. And you're like, oh, okay, well, yeah, it's doing something to the dog, right? What it thinks is a coyote in the background in order to suppress it. And then somehow it's recognizing, I don't know, the combination of the beaver and the deer as a wallaby, perhaps. And then it turns out that no, if you optimize it properly, again, so you use our new method, you find it's actually just a very sparse, small localization with a few pixels changed here. We'll flip it to something different. You don't actually need to do anything to the dog at all. And this is not what's driving the image classifier. So yeah, something else which came out of this is a big question. Like, if we have multiple explanations for something, can we learn which one's better? And here I'm going to completely gloss over the mathematics and say, if I give you two different explanations, right? So I can't ask you to say, give me the best possible explanation for a particular event, right? This is something which is not reasonable to ask people. But what I can do is give you two different explanations and say, which one do you prefer? Which is more helpful in the current situation? And what I can then do is I can use sort of like old machine learning techniques, such as ranking SVMs, to learn a new distance measure, which will tell us the most relevant counterfactuals for a particular situation. And basically what happens is we learn that given a particular data point and a particular context, this is the kind of counterfactual I should be giving people. This is what I should tell people is going on. So going back to the LSAT dataset, there were three different factors in there. There was your average GPA taken over 3 years. There was your law school entry exam, and then there was your skin color. And what happens is there's three different explanations you could offer people easily, right? So you can say, oh, well, you were predicted to do better than average. Some ways you could be predicted worse were, and you can give someone an actionable explanation, something which they can take away and say, like, oh, okay, well, if I work harder, if I reset the law school exam, this would happen instead. Or, yeah, if I reset the law exam, I might fail, and then I wouldn't be allowed in. You can give them ethically concerning explanations, which say, like, it really depended on your skin color. It's only because you're white that you were allowed in here. And you can give people explanations which they think are trustworthy. And it can say, like, okay, well, we looked at your school performance over several years, and because that was a solid 3.3, you were allowed in. If it had only been 1.6 on average, you wouldn't have been allowed in. And what you can do is you can learn an explanation for each one of these different contexts. So depending on whether people want to know that something is actionable, or to trust a classifier, or to know when something is wrong, you can learn to tell them what's most important. And this is interesting. So we took Amazon Mechanical Turk data, and what we found is it actually drove us away from simple explanations towards more complex but actionable things. So we started out, and like the best explanation we had to begin with was something like your cumulative grade point average was 9, and if it had been 8, then you would have been rejected. And after like taking people's preferences into account and what kind of explanation they preferred, you get stuff like, okay, well, if your GRE, particular test scores on entry had taken higher values, or if your English entry scores had been higher, then you would have been allowed in. And it comes up with the factors that are easiest to change in order to get an outcome you want. Something which is interesting is, so there's a common argument in philosophy that it's wrong to discriminate against people on factors they can't change. Right? And this is one of the reasons why racism and sexism are bad. It's not the only reason, but it's a reason. What we found is that factors which are preferred in actionability, so English is a foreign language, this is something which you can always improve. Right? You go away, you read more books, you watch more TV, you get more familiar with the language. It's something considered highly actionable, easy to change, and at the same time extremely ethically concerning to the people who were helping us with this. And so like explanations which are both ethically concerning and actionable both tended to change these factors. So we ran it on some other data sets as well. So credit scoring this is a common thing, right? This is one of the big uses for explainability, like whether or not you're allowed a loan, whether or not you're trusted by banks, basically. And this is something fundamentally banks want to give people automatic explanations that make them feel better about the decision that's been made, but don't open them up to any legal liability. What we found is there's basically no magic bullets here. So on these credit data sets, there is nothing which is actionable. It's like you don't earn enough money, you're not going to get a loan. And fundamentally, like this is not really something you can change. If you're lucky enough to get promoted, it tells you like, oh, now you can come back. But it's something which is very hard to drive towards and to change. So we found that actually trying to learn a classifier or learn a better explanation, which is more actionable for credit scoring, doesn't work. You can, again, people don't really care about trustworthiness either. We also tried this on COMPAS data, which is, this is deciding whether or not people should be allowed out on bail, and if they're at risk of reoffending, if they're allowed out. This is super depressing, actually, because going through this and you're asking people like, if I tell you to change this, could you do it more than if I asked you to change this? There are no changeable factors at all. The decisions as to whether or not you're at risk of recommitting do not depend on anything you do. It's like, what is your socioeconomic group? Where do you live? How old are you? And these are the main risk factors. And yeah, and there's nothing you can do about it. There is no way to actually dig yourself out of the hole these systems put you in. So we find that there are no actionable explanations. It doesn't matter what I tell you, you can't change anything. So it was actually really quite depressing, I think. For things like graduate school, it's like, yes, it's easy to give people explanations that can help them like actually get in and do better. But for a lot of the real world applications of algorithms, like there's nothing we can do to tell people. And at the same time, like we know that COMPAS is horribly racially biased, right? It's incredibly famous. There's been articles all about it. If you're black, you're at incredibly high risk of being marked down for reoffending, even though you're not likely to. Even the people that aren't likely to. But at the same time, like the explanations that we give people, because the factors hide race, right? They talk about socioeconomic status. It's like, what is your salary? Where do you live? These things, they're not apparently racist. They're not apparently sexist. So there's nothing we can tell people, like to say like this algorithm is racist, because it uses factors which are a proxy for race, but are not actually race. So in some sense, it's like, came into this like, this is a really exciting field. It's like we can give explanations for black box algorithms. And what we're finding is that these explanations, like, it may not be possible to help people. Like, there are some situations where they're great, they do the right thing. For other things, like, it just doesn't matter what you tell people. Like, this is how the system is, and this is what you're stuck with. Something else which was worrying is, this is pretty much my last slide anyway. So, yeah, you can change how people perceive algorithms, whether or not they trust them, without changing the algorithm at all, right? So I can keep my horribly racist classifier, and just by changing what explanations I'm prepared to give you, I can make you think it's fine. And as such, like, explanations, yeah, it's very much a two-edged sword. It's like, you can tell people what to change in the world, but you can also hide all the problems that we have behind them. And this is a fundamental issue, and it comes from the fact that, as I said at the start, like, these algorithms are too big to fit in your head. So either I give you this approximation, which glosses over some of the nasty stuff that I don't want to talk about, or I tell you something which is incomplete, and it hides the nasty stuff I don't want to talk about. And there's no magic bullet. There's no way around this. Cool. So thanks.